All right, welcome to chapter 9. We're going to see if we can't just go ahead and knock this out in one video because I think you're going to be pretty familiar with a lot of this from physical science or Gen Chem, so we'll try to make short work of this chapter 9. So we're talking bonding here, intro to bonding. Valence electrons are the outer shell electrons. The valence electrons are the ones that actually participate in chemical bonding, so they're mostly what we care about. Here's something hopefully you've picked up from last chapter. Group 1A elements have the NS1 configuration, so only have one valence electron. Your alkali earth metals have 2 valence electrons. Group 3As are going to have 3 valence electrons, 4As are going to have 4, 5As are going to have 5, 6As are going to have 6, 7As are going to have 7s. These are our halogens, and we know that they end in S2P5, and then you can go back S2P4, and that's all last chapter stuff. So hopefully that gives you an idea of how many electrons we're working with when we go to drawing Lewis structures. So here's a nice periodic table of just Lewis structures. Here you've got 1 valence, 1 valence, 1 valence all the way down, 2 all the way down, 3, 4, 5, 6, 7, 8. And hopefully you're familiar with that, except for helium, stable at, 1s2. And then weirdness in the transition metals. So hopefully that's old news. An ionic bond, you may have learned earlier in your life that it would be a metal and a non-metal. That's pretty much going to be true, and we're going to talk about why. So the electrostatic force that holds ions together in an ionic compound. Here we can look at lithium and fluorine. Lithium being a metal, probably going to be an electron giver. Fluorine having 7, probably going to be an electron taker. And we see that they form a bond by lithium becoming this positively charged cation, fluorine becoming the negatively charged anion, and lithium has, for all intents and purposes, given its electron to fluorine. So we see lithium was at 1s2, 2s1, be very stable if it could lose that 2s1. Fluorine is 1s2, 2s2, 2p5. Fluorine would be very stable if we could make that 2s2, 2p6. We'd have a stable outer shell there. And so that's what we do by making this bond. Lithium becomes 1s2, which is like helium's noble gas. Fluorine becomes 2p6, which is like neon as a noble gas. So you can break this into half reactions if you really wanted to. You could say lithium has 1 valence, and so it is going to give up that 1 electron. Fluorine is going to accept that electron, and its product will be the fluorine anion. And so we can kind of write it out like so. Lithium cation plus fluorine anion yields lithium fluoride, the salt, and that's what it would look like there. So hopefully old news. Here's something that might be new. Lattice energy is the energy required to completely separate 1 mole of solid ionic compound into gaseous ions. For the physics nerds in the class, you'll notice that this equation is the same as measuring electricity across a distance, which is kind of cool. Charges over radius, which is neat. So E is potential energy, Q plus is the charge on the cation, Q minus charge on the anion, R is the distance between the ions, and K is a constant. So we look at a couple compounds here and how different they are. And you can see that magnesium fluoride, lattice energy of 2,900, and then magnesium oxide, a lattice energy of 3,900. And that's kind of odd considering they're both, salts with magnesium, but oxygen is such a bigger number. And our answer for this comes from their charge. Here, magnesium has a +2. That's the cation, and fluorine is its anion. Now, it doesn't matter so much that there's 2 of them, only that their charge is a -1, and so its -1 would go over here. Now, magnesium oxide would be +2 for magnesium, -2 for oxygen, and so we're going to make those charges a lot bigger. It's going to make our energy a lot bigger, kind of a linear relationship there. Now, the other end of this equation is the radius, because as you bring 2 charges closer together, they're going to become a lot stronger, and so here we have lithium fluoride and lithium chloride, and the radius of fluorine is a lot smaller than the radius of chlorine. And so because fluorine is so close to lithium, we shrink that radius down, and our energy becomes greater. And so it really depends on both of these factors, the charges and their radius. Now here fluorine's charge is a -1, chlorine charge is a -1. So really we're comparing the same charges, the only difference would be the radius. All right, so lattice energy increases if we increase Q, or if we decrease R. So here's the Born-Haber cycle for determining lattice energy. It basically uses Hess's law to break reactions down into half reactions of their gaseous ions, and then combining gaseous ions into solids, and then you're combining, the enthalpy of one step plus the enthalpy of the second step plus the third plus the fourth plus the fifth. It's this very long, convoluted thing, which I'm sure is a lot of fun, and we are not going to calculate it. So I apologize for that. I'm sure you were looking forward to doing that. Here's a table that's kind of sort of useful. Lattice energy of a bunch of different compounds. You can tell that they're all, ionic, and then what their lattice energy is, and then how it's going to relate to their melting point. So our example of a useful ionic compound is sodium chloride, which is salt, and here you can see how it's used. This little chart's in your book too. 12% of the salt we have is used for meat processing, food canning, water softening, that kind of stuff. 3% domestic table salt, stuff you put on French fries and what have you. 4% goes to livestock feed. 17% melting ice on roads. 4% other chemical manufacture. A little bit goes into sodium carbonate, and then some goes into chloralkali processes, so other chemical processes, and that's 50% of all salt used, so that's a lot. There's a couple ways to get salt. Here they're mining salt, rock salt you might have heard it called. So actually down here, underground mining salt. And then here's kind of a cool method if you live by the ocean and it's really sunny, solar evaporation. Take the salt water, spray it out on a big flat hot surface, water evaporates, salt's left behind, you scrape up the salt. Kind of a cool idea. So let's switch from ionic to covalent. Covalent bond is a chemical bond where we're sharing electrons. Why would they share electrons? You probably already know the answer to that. Would be to become more stable. If he has 7 and he has 7, if they could share and both have 8, they'd be a lot more stable, and that's exactly what they do. And so we say first fluorine had 7, second fluorine had 7. Now by making that bond, they can both have 8, and they're a lot more stable. So to draw a Lewis structure, we just take those two bonded electrons, the shared electrons, we make 2 electrons one line, and then we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Hopefully you're very comfortable with those. If you're not, you need to become so quickly. So we call these guys lone pairs of electrons. They are grouped together, 2 and 2 and 2. That's a pretty stable place to be. You don't want to be one lone electron. That's really unstable. So we draw those as well. And then here we have a single covalent bond. One line shows 2 electrons being shared between 2 atoms. So a Lewis structure for something different. Water, we've got hydrogen, oxygen, hydrogen. We know hydrogen's in that first group, so we put 1 valence electron. Oxygen's in the 6A, so we go 1, 2, 3, 4, 5, 6. And then we can form bonds by kind of linking these 2 electrons together, sort of the way you could think about it. And so here we've pulled them closer together, and we've got 1, 2 forming a bond, 1, 2 forming a bond. They form single bonds only with hydrogen, because if it only has 1 electron, it certainly can't form double or triple bonds. So bear that in mind for the future. Now oxygen has 8, hydrogen has 2, and they've both accomplished noble gas configuration. So double bond. If you are in a chemical that can make a double bond, we can certainly do that. Here's carbon dioxide, where carbon has 4 valence and oxygen has 6. So if we can share 2 of the 6 on each of them, then we have 2 electron pairs that are lone. If we'd only shared 1, we'd have this kind of one lonely guy. He's not really that stable. So if we put double bonds there, carbon has what we call the complete octet. Oxygen has its complete octet because every bond counts as 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. We're stable there. All right, oxygen's got 8, oxygen's got 8, carbon's got 8. Got it. So there's double bonds. Triple bonds, not something you're going to see a whole lot of, but there are a couple elements that can form triple bonds. Super strong, super short bond. So if they shared 3 pairs here, nitrogen has 5 valence, and so if it can form 3 out of its 5 for valence, then we can only have 1 lone electron pair, and that's pretty stable for nitrogen. And so here's nitrogen gas. 1, 2, 3, 4, 5, 6, 7, 8. Each nitrogen has 8 electrons, and that's a really, really strong bond. So let's look at length of covalent bonds as something we can measure. You look at carbon and hydrogen, carbon and oxygen, and they're reasonably comparable. And then as you move down to triple bonds, their bond length should get quite a bit shorter, 116, something like that. General rule, double bonds should be a little bit shorter than your single bonds. Triple bonds should be a little bit shorter than your double bonds. That's kind of the trend. And so for bond length, triple bonds should be pretty short, 116. But that is going to compare or depend on a few other factors too than just the bond, electronegativity and that kind of stuff. So properties between, you look at, an ionic compound and a covalent compound, how are they going to vary? Their appearance, a lot of covalent compounds are like salts, so some sort of white solid. Here, CCl4 is a colorless liquid. Their melting points, you can see, are very different. You got to get salt pretty hot to melt it. This, however, will melt pretty readily. It's a liquid already. Then we have boiling points. It's a lot harder to boil salt than it is to boil carbon tetrachloride. Then we got heat of vaporizations are very different. Solubility in water. Salts are pretty soluble in water. Covalent compounds, kind of not so much. Salts, when they're dissolved in a liquid, are going to be pretty good conductors of electricity for ionic compounds. Covalent compounds, if you really pump enough electricity into them, they'll transmit a little, but they're pretty poor conductors. So, a polar covalent bond, if you have greater electron density around one of the atoms, it's polar. We call this electronegativity difference. Fluorine is much more electron greedy than hydrogen, and so while they don't share fairly. Most of that electron's time is going to be spent with fluorine, so we call that a polar bond. Hydrogen is going to be partially positive, fluorine's going to be partial negative, and we use the lowercase d delta for that. So we have fluorine as electron rich, hydrogen as electron poor. That's what it'd look like on a Lewis. And here's your delta. Delta negative means a partial negative charge here. Delta positive, a positive charge on the hydrogen. If you used crossed arrow notation, something I don't think we've talked about too much, you would draw it like so. There's the cross that shows it's positive, and the arrow that points to the negative end. So that's how you do crossed arrow notation to denote polarity for Lewis structures. So electronegativity, it's a term we've used a lot. Hopefully you remember it's the ability of an atom that attracts electrons into chemical bonds. Electron affinity is something that's measurable. That's the energy change. Chlorine's the highest. Electronegativity is not something that's really that measurable, but for us, fluorine is the highest. So here you have electronegativities of some common elements, and you'll be using this chart here pretty soon, and I'll tell you what page it's on. But here you can see electronegative is going to run about 0 to 4. Your metals, 1 and below. Alkali earth metals, 1.5 and below. It's really low electronegativities. As you move up and to the right, fluorine, chlorine, sulfur, and oxygen, you get really high electronegativities. These are the greedy guys. Fluorine and chlorine, 4 and 3. Oxygen, 3.5. They're going to want to take electrons. And so hopefully you recall this from a periodic trends chapter. Increase electronegativity, up a group, increase electronegativity to the right across a period. And so fluorine being located at the upper right is going to be our most electronegative, and of course we are leaving out just about all of our noble gases because they don't really want anything to do with electrons. We can get these guys to form a couple compounds, but it's pretty tricky. So variation with atomic number, here as you go across the periodic table, lithium to fluorine, it just goes up and up and up, and then as you go back down to the second group starting at sodium, you drop way back down to 1, and the trend is increasing again. And do remember that it's a trend, so as we move across our third group or family, or rather our third period, sorry about that, it's a trend. So you'd kind of have to say, if this were in something like Excel or something like that, and we did a best fit line, is it perfect? No, but our trend is sort of like that. And here our trend is sort of like that. So there's minor fluctuations, especially as we move into those metals and transition metals, but the trend is still, as you move across the period, the electronegativity is going to increase. So we can classify bonds by their difference in electronegativity. So if our difference is 0, we have 0 difference in electronegativity, like hydrogen bonded to hydrogen. they're exactly the same. Fluorine bonded to fluorine, they're exactly the same. We can call that covalent or nonpolar covalent. Now, if we have a difference that's greater than 2, that makes it ionic. But if we get in this place where we're greater than 0, so it's not hydrogen bonded to hydrogen, but we're less than 2, it's not lithium bonded to fluorine. We get in a place where we're sharing, but we're not sharing evenly. So we're not truly covalent, we're not truly ionic. What are we? Well, we're polar covalent. We share, but not fairly. And so as we increase our difference in electronegativity, we progress from covalent to polar covalent to ionic. And here's a chart that shows you chlorine bonded to chlorine. Their electronegativities are very close. And so these guys are about as covalent as it gets. So on the chart of percent ionic character, or basically how ionic are you, we're incredibly low. We're not very ionic. We move up to iodine and chlorine. They're close to each other on the periodic table. They have very similar electronegativities. So they are going to be greater than 0, but they're not truly nonpolar covalent. They're going to be a little bit polar covalent. We keep moving up and we get past 2. And we're seeing a lot of lithium and potassium coming into here. Our metals and our nonmetals, potassium and fluorine, and lithium and fluorine. Our electronegativity difference goes through the roof, and our percent ionic character gets really close to 100. Do we ever get to a point where lithium truly gives fluorine an electron and never sees it again, completely given away? Not really. But when you get up to that 85-90%, we say that's pretty ionic. So here's the way you could do this. You go to page 381 in your text, and you look at this periodic table with all these values on it. And you can look at the bonds and classify them as ionic, polar, covalent, or covalent. Now remember, the number we're looking for is 2. So the bond in cesium chloride, the bond in hydrogen sulfide, nitrogen gas, and then this chemical here, H2NNH2. You can look at these bonds and classify what they are. So take a minute, flip to 381, pause the video, see if you can do the first 2 on your own, and then we'll pick up from there. Okay, hopefully you had some good luck solving these. Pretty simple subtraction. So cesium, you look on your chart, it's going to be about 0.7. Chlorine's going to be 3. So you take 3, you subtract 0.7, you get 2.3. Now we're above 2, we're going to call that ionic. You take hydrogen and sulfur, and the hydrogen is bonded to the sulfur here. It's not hydrogen to hydrogen, so sulfur is 2.1, or rather, hydrogen is 2.1. Sulfur is 2.5. So our difference is only 0.4. So that would be polar covalent. Here we've got nitrogen bonded to nitrogen. They're exactly the same. 3 minus 3 is probably 0, and they're probably covalent, non-polar covalent. So that's how you can solve those things. When we write Lewis structures, this is something that we've done, I hope, a lot. You draw a skeletal structure of a compound, you show the atoms that are bonded to each other, and you put the least electronegative element in the center. When in doubt, throw carbon in the center. Count your total number of valence electrons, add 1 for a negative charge, subtract 1 for a positive charge, and complete an octet for all atoms except hydrogen, and boron, and beryllium, and sometimes sulfur, and a few other exceptions. But complete the octet when in doubt. If your structure contains too many electrons, you can start to form double and triple bonds to try to get us to that octet. So nitrogen trifluoride. Step 1, nitrogen's a lot less electronegative than fluorine, so put nitrogen in the middle. There's nitrogen in the middle. Surround them with 3 fluorines. Countervalence electrons. Nitrogen's going to be at 5. You can find that on the periodic table. Fluorine's going to be at 7. You can go ahead and throw those dots around there. So they said, okay, if there's 5 valence electrons, then there's going to be 26 valence electrons total, because we've got 3 times 7 for fluorines, 1, 5 for 1 nitrogen. So hopefully at the end of our product we get 26 valence electrons. Draw single bonds between nitrogen and fluorine atoms and complete the octets on their nitrogen and fluorine. Now, you should note that fluorine's only going to form a single bond because it's 2s2, 2p5. So it's already got 7 valence electrons. It only wants to gain 1 more, and it'll be stable. So don't try to throw any double bonds on fluorines. That's a bad strategy. Now, we complete our octets and we see what it looks like. Nitrogen's at 1, 2, 3, 4, 5, 6. So to complete its octet, we'd have to get 2 more, a lone pair, which is pretty stable. We complete our 6 around fluorine, and then we add them up. So nitrogen's got its octet, fluorine's got its octet, and here is a space filling diagram for nitrogen trifluoride. So let's check our number of electrons, see how we did. We got 3 single bonds, so there's 2, there's 4, there's 6. Lone pairs, we've got 10. So 1 lone pair, 2 lone pairs, 3 lone pairs, 4 lone pairs. You get the idea. It adds up to 26, and that's what we were hoping to get when we started out with this. So we're very probably right with our Lewis structure. Let's do a little harder one, a carbonate ion. And it tells us right away we're going to have a 2- charge, which tells me that when I'm filling in my valence electrons, if we end up with a couple more electrons than we should have had strictly with valence, we're probably okay. Carbon's a lot less electronegative, we put it in the middle. We surround it with its 3 oxygens, we count our valence. Carbon should have 4, oxygen should have 6, and since we have a -2 charge, we can kind of throw a couple extras in there. So we should end up at about 24 valence electrons, counting the same way we did before. So let's start out with single bonds and see what it looks like. So we threw single bonds everywhere. We'd have a lone electron pair here and 3 lone electron pairs around oxygen. Now, that's okay. I mean, we've satisfied the octet rule, but if we could get these 2 electrons in a bond, they'd be more stable bonded than they would be as a lone pair. That'd really be ideal. So let's take a look at this. We've got 8. So, strictly speaking, we've done okay on the Lewis thing. Are our number of electrons equal to the number of valence? Well, let's give that a count. We've done 3 single bonds, so 2, 4, 6. We've done 10 lone pairs again, so 10 times 2, we're at 26. We're supposed to be at 24, so this structure is probably not the best. Step 5, if we have too many electrons, we form a double bond and we recheck. So let's throw a double bond on one of these oxygens instead. And then we recount them. So now we've got 2 single bonds, 2, 4, 1 double bond, 6, 8, lone pairs, 2, 4, 6, 8, 10, 12, 14, 16. 4 and 4 and 16, we're at 24. That's what we thought we should be when we started counting this up. And so we know that we're probably correct here. Now, it might kind of bother you to look at oxygen and say, okay, 1, 2, 3, 4, 5, 6. Got it. Valence electrons bonded. But then here you say 1, 2, 3, 4, 5, 6, 7. Well, how does that work? Oxygen has 6 valence. How are we forming the single bond? How does this even exist? That's where that 2- comes in, that 2- charge. That's going to allow us to form these. So it gets a little confusing, but we can draw them. So 2 possible structures for formaldehyde. What if we get something where there's 2 ways to draw it? And we can really satisfy our octets with both structures. How do we know what's right? Well, we can look at what's called a formal charge, and it's the difference between the number of valence electrons in an isolated atom and the number of electrons assigned to the atom in a Lewis structure. So they give you a terribly convoluted formula in which to calculate this, and I'll show you a much simpler way. So their tough way to do it is the formal charge of an atom in a Lewis structure is equal to the total number of valence electrons in the free atom minus the total number of non-bonding electrons minus 1/2 the product of the total number of bonding electrons. Not a fun thing to calculate. Let me show you an easier way. The sum of the formal charges in a molecule or ion have to equal the charge on the molecular ion. So if we went ahead and threw electrons in here, we'd see carbon at 1, 2, 3, 4, 5, 6, 7, 8. That's not too bad. Oxygen at 1, 2, 3, 4, 5, 6, 7, 8. That's not too bad. If there's a way we could get rid of these, we would probably be a little more stable. But we look at having 12 electrons, and here we look at having 12 electrons. So we're kind of okay. Now they're going to show you a formal charge on carbon, and they're going to calculate it this way. 4 valence from your periodic table, 2 are the non-bonding electrons, that's these fellows up here, and then we're subtracting 1/2 of 6 as bonding electrons equals -1. Okay, let me show you an easier way. This is the way I like. When you look at carbon, we'll draw a little squiggly line through here. We're going to say, okay, if that's bonded, then we're going to say carbon gets 1 electron. That's pretty much his. Here, we're going to say, okay, if that's bonded, carbon gets 1, 2 electrons. That's pretty much his. Now, if carbon on the periodic table has 4 valence electrons, and right now, carbon in this molecule has about 1, 2, 3, 4, 5 valence electrons. Well, if he's got 5 now, then what's his charge now compared to the charge of 0 on the periodic table? Well, of course, it'd be a -1. Much easier than whatever in the world that is. Looks like a nightmare, okay? And it works. I mean, it works. It just looks awful to me. So let's do the same thing with oxygen, right? Let's see what we can do here. Pen, I guess should we change the color and be really fancy? Look at us. We are so high tech. All right, so we do the same thing here. We do the same thing here. We go, okay, oxygen, on my periodic table, you're at about 6. Here, you're at about 1, 2, 3, 4, 5. Well, if you should be at 6 electrons, and you're only at 5 electrons, then you have 1 less electron than you'd really like to have. So you're probably a +1. A lot easier than this thing. 6 minus 2, 1/2, blah, 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 +1. Cool, I got you the same answer just without trying to memorize that. And it's red and green. Merry Christmas. All right, so what else do we want to look at? Oh boy. Oh, cool. No, this is good. This is our other structure of formaldehyde. We got hydrogen, a hydrogen. They're bonded to a carbon. Right away, I'm not seeing lone electrons around carbon, so I kind of like that. Double bonded to oxygen. We've completed octets. This looks really good. We're sitting at 12. We're sitting at 12. And, oh, there's that little gem again. Wonderful. All right, why don't you count this up? And you tell me if you like it or not. All right, so carbon should be at 4, right? 1, 2, 3, 4. We just drew the squiggly lines in our head. Oxygen should be at 6, right? 1, 2, 3, 4, 5, 6. Their charges are 0, and we know enough about chemistry to say that's probably a good thing. We didn't memorize this goofy formula, but we know their charges are 0. So here's the formula. Blah, 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 0. So if we can have a place where our charges are 0, that is very probably more stable than a place where our charges within the molecule are +1s and -1s and +2s and stuff like that. Are they going to happen? Of course they are. But if we have the choice, we want to go with the more stable one. So for neutral molecules, the Lewis structure in which there are no formal charges is preferable to one in which we have formal charges. Lewis structures with large formal charges are less plausible than those with small formal charges. So if you have to choose between a +1 and a -1, or a +2 and a -3, choose the smaller numbers, +1, -1. If you're looking at Lewis structures that have similar distributions of formal charges, the most plausible structure is the one in which the negative formal charges are placed on the more electronegative atoms. It's wordy, but that should make sense. Fluorine and chlorine should not be a +1. Make sense? They're really electronegative. They should be negative. So here we've got one. We've drawn a structure where we had the -1 and the +1. That's the first possible structure of formaldehyde with satisfied octets. And we have another structure for formaldehyde with charges of 0. So which would be the most stable? The one with the charges of 0. So there's our answer for what is the most likely Lewis structure for formaldehyde. So let's look at resonance. 2 or more Lewis structures among a molecule that can be represented accurately. So here we have ozone, and we look at it and we can say, well, we could put a double bond here, or we could put a double bond here. Now, you know molecules exist in 3-dimensional space, so is this truly different? Well, I don't know, not really. I think if you just rotate this over, you have this. But we use resonance anyway, because truly it's like 1.5 bonds and 1.5 bonds, and that's kind of a nightmare to draw, so we use resonance instead. And we say that it's kind of resonating constantly between these two structures. So we satisfy octets when we do the resonance structures, just like any Lewis structure. So we look at carbonate, we say, okay, carbon in the middle, 3 oxygens around it, we know it has a 2-, we've drawn it before, we satisfy octets for carbon, we satisfy octets for oxygen, and then to draw its resonance, we just start putting those double bonds in different places. So the other one we could put double bond on the left, and the other one we put double bond on the right, and there's all 3 possible structures for a carbonate ion. Resonance. All right, exceptions to the octet rule. Incomplete octet, beryllium. It is happy with 4. Boron, happy with 6. That's pretty much what you need to know there. You get a few that can go weird numbers. NO. Yikes, look at that guy. Screams instability. But it's a thing. It exists. We have to draw it. Expanded octets. Sulfur hexafluoride. You look at this. It's a thing. It exists. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're not following octet at all, but it's a thing. It exists. What are we gonna do? You gotta draw it. So there's some weird stuff. Let's look at enthalpy. The enthalpy change, which we've already talked about enthalpy a little bit, required to break a particular bond in 1 mole of gas molecules is the bond enthalpy. Here we have hydrogen gas. We're breaking it into just monoatomic hydrogen. Here we have chlorine gas. We're breaking it into just a single chlorine and a single chlorine, and we're seeing how much heat is absorbed to break that bond. Here we have hydrochloric acid, same thing, oxygen. Now we're looking at a double bond here. So to break that, you see that number 498, we're getting a little bit higher here. It takes a little more energy to break that double bond. Nitrogen and nitrogen is a triple bond. And the triple bond, you can see its bond enthalpy is huge, 941 kilojoules. And so bond enthalpies are generally going to be your single bond. It's going to be a lot lower than the double bond. It's going to be a lot lower than the triple bond. It takes a lot of energy to break a triple